let us start this lecture 9 with a thought process I have taken from a poem known as Question. You know, like we ask a lot of questions when we are particularly babies or small child, but as you go along we will start not asking questions, right, and maybe it is because of social effect or the society what we are living in. Therefore, it is very important to ask questions for pursuing the scientific and engineering work, particularly or any other work. Therefore, I want to say that it is question can never be silly, it can be a beautiful lily in the garden of knowledge, that is the truth age after age. And whatever science and technology what we see, it has come out of asking questions. Let us look at what really we studied in the last lecture. If you recall, I asked a question at the end, that is, why do we look at the isentropic relationship, although it is very restrictive in nature. Of course, before that we derived the Bernoulli's equation for compressible flow and also the incompressible flow, right. And generally the Bernoulli's equation for compressible flow is being used, but it cannot really be used for the compressible flow, right. And then we moved into isentropic flow, where there will be no dissipation, that means no change in entropy, and also it will be adiabatic. So, I guess you might have thought about the question I had asked in the last lecture, that why really we will have to look at isentropic flow, which is quite restrictive in nature, right. Can anybody tell me why it is so? Let us consider a flow, right, in a converging duct, what we have seen, right. Let us say there is a flow which is coming over here, and what will happen? It will increases, because there is a change in what you call velocity between the station 1 and station 2, right. Now, what is happening? The flow is accelerating, and where really this dissipation will be occurring. Dissipation means what? There will be kind of friction. So, friction will be there, what you call in boundary layer here somewhere, right. And unfortunately, I have drawn a very thick one, but it is very thin, right. If I just remove it, you will see that it will be in very thin, right. And where there is a likelihood of friction will be playing a role because of boundary layer, and also on the upper surface, because it is circular. So, it is on the over the internal surface area, it will be there. And whereas inside this flow, whatever inside, it will be not subjected to any what change in entropy, because we are assuming the flow is to be uniform, right, and also there is no gradient is occurring for entropy to occur. Particularly, if you look at, there is no temperature gradient, we are not adding any heat, right, or we are not having any diffusion, mass diffusion, where the entropy can also change because of mixings, right. And then naturally, we are not adding heat, so it will be adiabatic. So, there is no dissipation in the major region of the flow, then we can consider the flow to be isentropic in the major portion of the flow, except near in this boundary layer which is a very thin. What will be the thickness of the boundary layer? It will be order of few mm. Of course, that depends upon inlet Reynolds numbers and up to talk about or the fluid velocities. As it is accelerating, it will be very small as compared to a decelerating flow, right. So, therefore, as most of the propulsive devices are what you call can be considered propulsive devices like rocket nozzles or a diffusers or a even turbine blade flow through the turbine compressor. To some extent we can consider it to be an isentropic and carry out analysis for that. So, there is another concept what we would like to look at, which is the stagnation point. What do you mean by this stagnation point? Let us consider a flow over an aerofoil. I have shown aerofoil here, and flow is coming uniform velocity little away from the aerofoil. And keep in mind that air is flowing over this aerofoil, right, at a velocity, inlet velocity or upstream velocity of 100 meter per second. Now, if this fluid will be taking, it will be going in a streamline kind of thing. If I take this fluid velocity over here, if you look at the leading edge, it will come to a what you call standstill, right. So, fluid element has brought to 0 velocity, right. And if I take of course somewhere here, then fluid will go over like this, and similarly on the lower region another thing. And now, when this is brought to the 0 velocity, right, adiabatically and also reversibly, then we call it as an isentropical. That means, if the fluid element is brought isentropically to the 0 velocity, then we call it as a stagnation point or a stagnation properties. That means, if I am considering as a pressure, it will be fluid experience, like fluid will be stagnation pressure. And if I apply under this condition the first law of thermodynamics, right, that is the energy equation, that became S T is equal to H plus V square by 2. What it indicates? It indicates the total enthalpy is equal to the static enthalpy plus V square by 2, right, that is your dynamic energy, right. And if I assume a calorifically perfect gas, that means what? The Cp is not a function of temperature in this case, that means H will be basically Cpt, right. That is your calorifically perfect gas. Then I can write down that Tt is equal to T plus V square by 2 Cp, right. What I am doing? I am by definition I am saying H is equal to Cpt, right, and then putting it here, that is a total, and then here also it will be what you call Cpt, and then if I divide it, then across this both the left and right hand side, I will get Tt is equal to T plus V square by 2 Cp. So, what is this term? This we call it as a T, this one we call it as a, this term we call it as a static temperature, and this Tt we call it as a total or stagnation temperature, and V square by 2 Cp we call it as a dynamic temperature, right. What do you mean by this static temperature? Can anybody tell me? That means, when the temperature experienced by the fluid element can be termed as a static temperature. In other words, if I put a sensor on the top of a fluid element, right, which is moving at the local velocity, right, what it will be experiencing? It will be experiencing the bombardment of the molecules on the top of it. That is basically the temperature, the kinetic energy, what it will be experiencing, right. So, that is known as static temperature, and as it is moving at a certain velocity. So, therefore, that velocity will be nothing but v square by 2 Cp is basically the dynamic temperature, right. So, and if you look at similarly, we can define also the total pressure, total density, like that. Are you getting my point? So, what is this meaning? This equation, if you look at S T is equal to h plus v square by 2. What is saying? That means, if I take a station 1, if I take a particular station, let us say 1 and the station 2, then what I will get, right. For example, I am looking at a nozzle like kind of things, if I am taking this is 1, this is 2, right, station, and there is a flow which is occurring, right. If I look at H1 plus V1 square divided by 2 is equal to, I can write down H2 plus V2 square by 2. That means, and is equal to Ht. Can I say this? That means, what is saying? The total enthalpy is remaining same between the station 1 and station 2, right. So, that means total enthalpy is remaining same, provided the flow is steady and whether it will be inviscid or not. It will be inviscid, then only, is it so? But so far energy equation is concerned, we are not worried about whether it is inviscid or not, right. And then if it happens to be like that, means total enthalpy along a streamline remain constant, right. If it is uniform velocity at the upstream region, that means I can say that along with any streamline the total enthalpy remain constant. That means, along the whole domain the total enthalpy will be remaining constant, provided the flow is steady, right. Okay. And it need not to be one dimensional, right, because my streamline can be two dimensional as well, right. So, therefore, it need not to be one. This is the profound statement. You may say we have derived for one dimensional flow, now we are talking, but you can interpret that. But keep in mind that total temperature, total pressure, is it really a quantity which you can measure, or what is the so big about it we are talking? It is actually derived quantities, right, and it is quite difficult to measure as such, right, because you need to bring the fluid isentropically, right. So, therefore, but however, at two locations the flow need not to be isentropic, but however we can use this relation locally, that is very important point. So, I have already talked about this, like T represents the temperature and ideal gas attains when it is brought to rest isentropically. And having said this, about this stagnation point properties, let us look at the total property ratios, and that is equation 10 became like this. What I will do? I will just divide this T T by the T temperature, and also the right hand side of this equation by the static temperature T. So, what I will get? I will get T T by T is equal to 1 plus V square divided by 2 C P T. And for a calorific perfect gas, I can write down, that is C P is equal to gamma R divided by gamma minus 1. I have done that here, right, gamma R T divided by, when I take this gamma minus 1, that became in the numerator, it will be gamma minus 1. That becomes 1 plus gamma minus 1 divided by 2 V square divided by gamma R T. So, what is this gamma R T? Gamma R T is basically speed of sound square, and where gamma is C P by C B, then I can write down T T divided by T is equal to 1 plus gamma minus 1 divided by 2 m square. What is this m? M is basically Mach number, which is the ratio of velocity and speed of sound. And similarly, we can use the isentropic relationship for the pressure and find out a relationship between the pressure ratio in terms of Mach number from the temperature. If you look at this, is a simple expression what we had derived in the last lecture, P T by P is equal to T T by T power to the gamma divided by gamma minus 1. In place of T T by T, I have put this expression, that is 1 plus gamma minus 1 divided by 2 m square, right. So, if you look at this expression, you should keep in mind, however, these isentropic relationships are available in the isentropic table. So, what I am expecting that you should keep in mind, and what it indicates? It indicates that this properties ratio, like temperature ratio and pressure ratio, right, will be dependent on the Mach number. That means, it will be dependent on the flow, and also it will be dependent on the kind of fluid. For example, gamma will be dependent on the type of fluid is being used. So, let us consider what is the implication of this temperature. If I consider, let us say, a aircraft, an aircraft is at an what you call altitude of 0, and it is moving at velocity of 100 meter per second, and temperature you can take 288 Kelvin, and the speed of sound will be 340 meter per second, and the Mach number will be 0.28, and when I calculate V square by 2 C P, it will be 4.98, roughly 5 Kelvin, and T T is become 292.98 Kelvin. If you look at it is 288 and then add this temperature, you get this. But whereas, if I go for this altitude 10, where the temperature is lower down, that is 2 to 3 Kelvin, and your vehicle is moving at a higher velocity, that is 500 meter per second, the speed of sound is reduced, that is 299.3 meter per second, and the Mach number is 1.67. But what is happening to this V square by 2 C P? It has increased, right, and as a result, the total temperature T T 347.38 meter per second, 347.38 Kelvin, whereas the actual temperature, static temperature, this is the static temperature, right, T K, the first row, that is 223. What we can, infer from this example? Can anybody tell me? Because these are the data, right? I have just put some data in front of you. I want to see what you could observe and tell me. So, what you can look at it is actually 5 Kelvin here, V square by C P. That means, the temperature difference between total temperature and static temperature is only 5 Kelvin. Now, what will be the percentage if I neglect, say that I am not interested, the total temperature will be almost equal to the static temperature. I need not to worry about compressibility effect, you can say that way, or the change in the temperature, right. But however, in this case, because why I am neglecting it here, the percentage of error I will incur by not considering the flow or the dynamic head will be what? It will be around something maybe 2-3%, right. Whereas, here if you look at in the other case, that is where the static temperature 223 and the total temperature 347, right, then what will be the effect? I cannot neglect, because it will be almost around 56% error if I will neglect that. So, therefore, it is important to consider these kind of things, particularly at the high velocity and also the high altitude, because the speed of sound is changing. Suppose you the case in the same altitudes at the sea level, that is 0 kilometer, and you are considering the speed of sound could have been 340 meter per second, right. So, therefore, this term could have been like reduced, because this it could have been not 1.67 with the 500 meter per second, it could have been maybe little lower, and it goes by square this expression. So, therefore, one has to look at it and be careful while doing. Keep in mind that this is the stagnation properties, or the is very important concept, which will be useful when you are analyzing. As I told that even though flow is non-isentropic, we can use it, because we can evaluate the total temperature locally and can use it. I will take some maybe example and show that where it will be useful, right. So, let us take an example, like air is flowing through the duct with an inlet velocity of 200 meter per second, pressure 0.1 megapascal, temperature 298 Kelvin. We need to determine the stagnation pressure, temperature and inlet Mach number, which is a very simple questions, but I just want to say that you need to use equation, right, whatever we have derived, and then velocity, if you look at given 200 meter per second, pressure is 0.1 megapascal, temperature is 298 Kelvin. And we need to find out total or the stagnation temperature. We know that T T is equal to T plus V square by 2 C P, right. For air, we know we can evaluate the C P as gamma r. Keep in mind that this is the specific gas constant, R is equal to R u divided by molecular weight of the particular gas, particular for air it is being considered. So, therefore, it turns out to be 1005 joule per kg Kelvin, right, and sometimes you will find 1.005 kilojoule per kg Kelvin, right. And when you substitute these values, you will get 318 Kelvin. This you just substitute in this equation. We can find out, instead of P T by P, you can write down T T by T power to the gamma minus 1 into the P, and then you will find out, substitute this T T by T, which we have already evaluated, right. T T is 318 Kelvin, T is the static temperature 298 multiplied by 0.1, you will get 0.16 megapascal. And of course, the Mach number you can evaluate very easily, because you know the velocity 200 meter per second and the static temperature already known to you. So, you can find out it, substitute these values V divided by gamma R T, and then it turns out to be 0.57, that is the Mach number. Keep in mind that these things you can evaluate very quickly using isentropic table, but however, I would urge to keep this small formulas in mind, so that it will be helpful for you to visualize and also solve problem in the exams whenever it will come, right. And let us look at the variation of T by T T and P by P T with the Mach number, and we will be using this expression, which we have already derived, and for the temperature ratio and pressure ratio, right. And when we put this values of Mach number per gamma is equal to 1.4, I will get a plot like this. Like means, if you look at this line is corresponding to the T by T t, and this the lower one, right, it will be corresponding to P by P t, and with the Mach number. What you could observe from this curve, which we have just used this equation 11 and 12, substitute the value of gamma, which we have taken 1.4 for air, and Mach numbers we have varied, we have created this plot. But it is just saying that it is changing, it is decreasing with the Mach number, right. That means, what is saying that when the Mach number is equal to 0, that becomes equal to 1, right, and it is decreases very less in the near region when the Mach number is something 0 to 0.5 kind of things, right. And of course, the at the Mach number 1, the change is quite drastic, because slope changes. Of course, the slope in case of the pressure ratio is much steeper than that of the temperature ratio, right. So, if I take this Mach number is equal to 1 line, and this will be basically sonic flow, and this will be supersonic flow. Of course, we have earlier discussed about transonic flow, where it will be between 0.8 to 1.2 Mach number, we call it transonic flow, right, which we have not indicated. But what is indicating this? That means that in certain regime, particularly in the near to the Mach, what you call low Mach number, it is not changing at all, right. So, whether we can call it as a compressible flow or not, we need to look at it, right. So, what is the criteria we have used? In other words, when is a flow compressible, or when we can label a flow to be compressible? How I will go about it? If you look at your definitions, what we discuss maybe 2-3 lectures back, right, we have came to conclusion, or we have come to conclusion that there will be change in density will be very, very small. If there is a change in density is small, then it is incompressible, and if it is more than the 5%, then we call it as a compressible. So, therefore, we need to look at the expression for a density ratio, that is rho t divided by rho is equal to 1 plus gamma minus 1 divided by 2 m square power to the whole 1 over gamma minus 1. So, what we will do now? We will take this gamma 1.4 for air and vary this Mach number and see what we are getting. We are getting rho by rho t is changing with respect to Mach number, right. And if we will use that criteria, that change in density should be less than the 5% for flow to be incompressible, right. That means, that is the we will have to take. Let us say that when we say that density changing by 5%, that will be, it will be 0.95, right. So, if I take this 0.95 this density ratio, and I will get a point, and then draw this point from a line from over here down, just to look at what is the Mach number. This Mach number will be around 3, to exactly, to say it exactly, it will be around 0.32, right. That means, this portion we can call it as a compressible flow, and this portion we can call it as an incompressible flow, from the practical point of view. But if you look at the name incompressible, then when I will get the flow to be incompressible? Only when Mach number is equal to 0. That means, change in density is equal to 0. Is it really possible to have an incompressible flow? Actually, incompressible flow is a myth, right. If you look at the strict definition of incompressible flow, change in density will be equal to 0. So, therefore, if you look at that means, at the Mach number 0, right, I will get rho by rho t is 0, that means change in density is 0. So, therefore, there is no flow. So, there is no incompressible flow as such, but in practical purposes we will be using in this regime when the Mach number 0 to 0.3 or 0.32, then we can call it as incompressible flow and use the governing equations for incompressible flow, which is quite simpler or simple as compared to the compressible flow. So, therefore, we can consider as a incompressible in this regime, because the whatever the error we are making, it is within something 5%, and that is good enough for us to make the analysis simpler or simplify it. So, therefore, we will be using these definitions, or basically it is a thumb rule. There is nothing sacrosanct about it, but we use it for a practical purposes. So, let us look at this isentropic and actual stagnation state, right. We have already discussed that this is basically for a like a temperature. We have seen that T t is nothing but T, that is your this point, that is static temperature, plus V square divided by 2 C p, right, when it is flow is static, flow is stagnation, flow is isentropic, right. That means, the total temperature is equal to static temperature plus V square by T, and this line, that what I have shown here, is basically static pressure line, and this is your static total pressure line, this curve what I have shown, this is the curve. Okay. Now, for this the entropy, that is the total entropy, remains same as that of the static entropy, right. So, if you look at this, total entropy is same as that of the static entropy, right. But in the actual stagnation point, that means, when it will be, it can be adiabatic, but however, entropy will be different, right. That means, if I consider this point, this is my actual stagnation point. However, if I consider a calorifically perfect gas, that will say that T t at this point is same as the T t at that point, right. In other words, what I am saying? I am saying the total enthalpy is remaining same, whether it is a stagnation, isentropic stagnation, or it is a non-isentropic stagnation point, right. But however, in this case, the entropy of actual is greater than the entropy of what you call of the isentropic flow, right. For non-isentropic flow, entropy will be, you can say this is basically T and then T here total if you take, then it will be greater. Because of what? Because of dissipation, and let us say there is a boundary layer or something like that, and you are having. But what happens to pressure? Pressure will be, actual total pressure will be lower than the isentropic total pressure. Why? Because of dissipation, there will be reduction in the pressure. So, therefore, what I want to conclude of this, that these stagnation properties can be used locally even for and non-isentropic flow, right. Although there is some kind of entropy change is there, right, we can use it very easily, right. Even if there is a heat addition, we can also use it, but locally it is correct. Therefore, it is a defined quantity and it gives a very good idea about the flow without really getting into complexities involved. That is the beauty of this stagnation what we call properties. So, let us look at another effect, that is the aerodynamic effect, which we have already looked at in one example, but let us consider an example flow over a high speed space vehicle. If you look at this is your high speed vehicles and you can see these regions which is quite burning kind of things here, very color is a kind of burning. Why? Because it is coming at a very high velocities, right. Mach number will be order of more than maybe 5, right. Particularly the re-entry vehicles or the intercontinental ballistic missiles, the Mach number will be order of something 25. So, in that case the heating, the dynamic head which is converted into the temperature at this point, because these are the stagnation point where the fluid cannot penetrate into the body. So, by considering this enthalpy equation at 2 points, we can determine, like let us say there is a point over here and then you are going point, let us say this is 1 and this is 2, you are moving like this, then H 1 plus V 1 square divided by 2 is equal to S 2 plus V 2 square divided by 2. I can say, I mean like this is, let us say flow is coming over like this, right. And if I take an calorifically perfect gas, I can write down T 2 minus T 1 is equal to delta T, that means change in temperature, right, will be equal to V 1 square minus V 2 square divided by 2 C p. If I substitute these values, let us say V 2 will be 0, right, and V 1 is maybe 1000 meter per second, it is not a very big Mach number, but however, you can see that the change in temperature is quite high, 497.5 Kelvin, right. Okay. So, it is quite high to be considered the effect of aerodynamic effect. What is happening? The kinetic energy, change in kinetic energy has been converted into the enthalpy, change in enthalpy, as a result there is increase in temperature. So, what we have looked at is that basically stagnation properties and then how it will affect and other things, but what we are discussing is compressible flow. In case of compressible flow, sonic flow is a very important concept which we must look at it. What is that? That is the flow at which the velocity of the flow is equal to the speed of sound, right. So, let us consider a fluid at a point is accelerated to the speed of sound adiabatically. Of course, we are considering adiabatic, there is no heat added inside or no heat is going out of the, whenever you are considering as a streamline, right. So, then what it is? Then V is equal to A, but question arises what will be its properties, because we will be more interested about the properties, right. Properties means pressure, temperature, density and other things. So, what are those things? We need to understand, right. So, for that we will start like whatever the we have derived of stagnation temperature and static temperature ratio, that is 1 plus gamma minus 1 divided by 2 m square, right. This we have already derived. If I put this V is equal to 1, V is equal to A means what? It is Mach number is equal to 1, that is your sonic, right. So, if I substitute these values over here, what I will get? That means this m is equal to 1, that means this becomes 1, right. And then this term will be basically gamma plus 1 divided by 2. This became gamma plus 1 divided by 2. Am I right? Because 2 plus gamma minus 1, it became gamma plus 1 divided by 2. So, then I will get an expression T by T T is nothing but 2 by gamma plus 1, okay, right. Similarly, I can get P T by P ratio, and I will get also this is P T plus 2 divided by gamma plus 1 power to the gamma minus 1, and similarly density ratio, it is rho star divided by rho 2 by gamma plus 1 power to the gamma minus 1. And these, keep in mind, this star I am using, this star corresponding to the sonic conditions. That means, all properties at the sonic conditions are denoted by star, right. So, if I substitute a gamma value for air, that is gamma is equal to 1.4, I will get T star divided by T T is nothing but 0.832, and P star by P T is 0.528, and rho star by rho T is 0.634. Keep in mind that the highest is your this value for temperature, then of course density, then it comes the pressure, because these are the coefficients, here it is a which will be better. So, similarly, we can define a term known as characteristics Mach number m star, that is basically the velocity, and the a star is the speed of sound. Might be looks to be odd, a is always the speed of sound, but why it is, right, that question might be coming into pictures, right. For example, there is a fluid which is subsonic. If I take this fluid to the sonic condition, right, that means I need to accelerate the flow, right, okay. And then corresponding to the local speed of sound I need to consider, and then that is the sonic velocity. Similarly, if it is the fluid is supersonic, I can decelerate the flow by using a diffuser to the sonic condition, then I will talk about that is there, but that means it is a fictitious local speed of sound. So, a is the speed of sound at sonic flow condition, then of course, a star will be equal to root over gamma r T star, that means corresponding to these values, right. So, that has to be considered. So, a star is not actual local speed of sound, it is the kind of imaginary corresponding to a particular velocity. So, this is a very important concept which you should try to assimilate it and have a feel for it, and as we go along we will see more about it. So, let us look at special forms of energy equation, and we will revisit this again adiabatic for adiabatic steady one dimensional flow, and if we invoke this first law of thermodynamics for a control volume becomes Cpt 1 plus V 1 square divided by 2 is equal to Cpt 2 plus V square V 2 square divided by 2. What I will do, if I put this for a calorific value, calorifically perfect gas, then Cp of course, I have taken, because keep in mind this equation is valid for only calorifically perfect gas. So, if I take the values of Cp and express like in terms of gamma and r, it become gamma r T 1 divided by gamma minus 1. Similarly, for the right hand side station 2 gamma r 2. What is this? This is basically your speed of sound square a 1 square. Similarly, I can write down this as a 2 square, right. And then I can look at as a 1 square divided by gamma minus 1 plus gamma 1 square divided by 2 is equal to a 2 square divided by gamma minus 1 plus V 2 square divided by 2. And let us consider the station 2, let us say it has come to a stagnation point, that means V 2 is equal to 0. If I will do that, then I will get this expression as A 1 square divided gamma minus 1 plus V 1 square divided by 2 is equal to A t square divided by gamma minus 1, because this term is equal to 0, right. So, A t is the total speed of sound associated with the same point. Keep in mind, it is related to the same point, that, right. So, if it is so, I can consider, if we consider the 2 station along a streamline, the equation 17 becomes A 1 square divided by gamma minus 1 plus V 1 square divided by 2 is equal to A 2 square divided by gamma minus 1 plus V 2 square divided by 2 is equal to A t square divided by gamma minus 1 is constant. What it indicates? That means, these term remain constant along a streamline between the station 1 and 2 in this expression, or it will be remaining constant along a streamline. As I told you earlier, that if the streamlines are emanated from a uniform flow at the inlet, right, then naturally along the whole domain, this A t will be remaining constant, kind of things. So, let us consider the station 2 as a sonic condition, V is equal to A star, then equation 8 becomes like A 1 square divided by gamma minus 1 plus V 1 square divided by 2. I am saying this is the V is equal to A star. So, if it is star, this becomes star. So, that becomes if I just add this together, I will get gamma plus 1 divided by 2 gamma minus 1 A star square, right, and which is equal to basically constant, you can say. So, therefore, I can generalize and say that A square divided by gamma minus 1 plus V square divided by 2 is equal to gamma plus 1 divided by 2 gamma minus 1 A star square. And of course, between 2 station I can write down equation 9 as same, and if I compare this equation 18 and 20, this equation, I can say that A t square divided by gamma minus 1 is equal to gamma plus 1 divided by 2 gamma minus 1 A star square. I am just comparing, because like 18, this portion is same as this. So, therefore, this same as that. That means, this portion is same as that portion I am writing. So, what it indicates? A t and A star remains constant along a streamline. It will be remaining constant. So, this is a very important what you call concept, which we will be using as you go along, and I will stop over here. Then next class we will be looking at also the sonic flow, continue from here and see that what we are getting. Then we will be moving into quasi one dimensional flow. Okay. Is there any question you people want to ask? Any doubt? There is no doubt, then we will stop over here.